Let's finish up this video. We just learned how to calculate torque using the second definition of torque equals Fd, and I just mentioned that if the object is diagonal, it's usually easier to use this definition, in my opinion. So we'll do this example and then talk about net torque to finish up this video. This example says signs are suspended from equal length rods on the side of a building. The mass of the sign is given in each figure. Rank these situations on the basis of the magnitude of the torque the signs exert about the point at which the rod is attached to the side of the building. So what this is saying is that the pivot point is where the building is. So that's the point about which the object is being rotated. It's the axis of rotation. So we're trying to find the torque exerted by each sign and then just rank them from biggest to smallest. So got some more room here. Let's do one at a time. So just good practice. This is called a ranking exercise, and it lets you practice a skill several times. The first one, so we have to figure out, well, how we're calculating torque. Are we going to use F perpendicular R, or are we going to use Fd for torque? Let's try Fd because the object is diagonal and the force is vertical. So the force in each case is the weight of the sign pulling down. The weight is mg. Now, g is going to be the same for each one, so I'm not even going to use it in my calculations because we're just comparing numbers here. We don't have to get exact values. How do we use Fd for part A here? We need to get comfortable using that moment arm. So I'm going to redraw it here where the force is going down, straight down. This is the weight of the sign pulling down. So the moment arm, you extend that force line, then you draw the shortest distance from the pivot to that force line. It hits it perpendicularly. That's D. And we have this angle over here, so it's the same one as this one. That's 30. So you can see that D is going to use the sine of the angle. So D is going to be R sine of 30. And then we're going to multiply that by the force, which is the weight mg. So it's going to be torque equals the force, which is m, 50 times g, times r sine 30. R is the length of the rod, which is the same length for all cases. So we don't have a number, but that's okay. G is 9.8. We could plug it in, but we don't need to. Let's take a look at B here. We have the sign here. The weight is pulling down here. And this time the force is perpendicular to the object being rotated. So in that case, you can use either definition because F perpendicular is the same as F, and D is the same as R, right? This R is the shortest distance to the force line, so R equals D, force equals force perpendicular. You can use either definition. So the torque is going to be the force, mg, which is already perpendicular, times the distance r. So the mass this time is 100, so it's going to be 100 g times r. Let's keep going. So you see how ranking tasks, you get to practice this several times. This one is very similar here, but the angle is different. Now the angle is 60 degrees instead of 30 degrees. The mass is still 50 like case A. So we're going to use the same definition as case A. The only difference is that D is going to be r sine of 60. D is this distance right here. So the torque is going to be 50 g r sine 60. And lastly, part D, we have one very similar to B. The difference now is that we have 90 kilogram for the mass instead of 100 kilograms. So the torque is going to be mgr, the weight times the distance, and it's going to be 90 gr. So now we have to rate these. So they all have g in a torque, so we don't care about g because it's affecting all four the same way. Now sine of 30 times sine of 30 is equal to half, and half times 50 is 25. So this means that this is equal to 25 gr. And over here, letter C, sine of 60 times 50 is equal to 43. So this is 43 gr. So the g doesn't matter, the r doesn't matter, that's why they didn't give us the length of the rod here. Now we can rank them. B is the greatest, followed by D, 90 gr, followed by C, which is 43 gr, followed by A, which is 25 gr. So this is just an example to practice using the definition of torque. The last thing I want to talk about in this video is net torque, just because we're going to be using it very soon. Net torque just means the sum of the torques, just like net force is the sum of all the forces. So if we have an object and there are several forces acting on it, and you're trying to find out how much torque is being exerted on this object, well, you just find all the torques individually and then add them up. So let's do a conceptual example for this, and then we'll see this actually come up in some equations in a video coming up. But the last question for this video, it says, which third force on the wheel applied at point P will make the net torque 0? So what in the world, right? So first of all, there's a force here which is acting at the pivot point, and then there's a force over here. So this point is fixed. So one note that is very important about this problem is that when a force acts at the pivot point, it doesn't cause any rotation. That means that force does not exert any torque. How do we know? Because torque is force times distance, or F perpendicular R. The force has to be applied at some distance from the pivot point. When the torque is at the pivot point, when it goes through that pivot point, that distance is 0, the torque is 0. So that's a note that you want to make. When a force is applied at the pivot point, it does not cause any rotation. So I'll write it down. Force at pivot point causes no rotation. So this force over here is going to cause a counterclockwise rotation, and that force is acting at this distance here. That's the perpendicular distance to that force. So you would just multiply F times D to find the torque. So how are we going to have a 0 net torque? Well, we need a force over here that will cause a clockwise rotation to balance out this one. So that means that we're going to have a force that goes this way, straight up, and it's going to be at this distance away. So you see how this force is going to have to be bigger than the horizontal force, because the distance here is shorter and torque is F times D. So if you have a shorter distance than over here, you're going to have a greater force than over here. So the best answer here is A. So that's the end of this video. We just did an example using the second definition of torque and talked about net torque. We're still going to do a lot more work with torque, especially in Unit 3 when we talk about static equilibrium, but we're going to see it more in the next few videos when we talk about Newton's second law for rotational motion.